So in this lecture we will see an example on how to solve an tapered elastic bar using finite element method. Okay, so the problem which is given in the following manner. So this is the tapered bar, and in this tapered bar the area which is varying as a in this manner. Okay, and this end is being fixed, so the displacement is 0, and we are considering x is equal to 2 at this end and x is equal to 6 at this end. Okay, x is varying in this direction, and the elastic property which is 8 Pascal. Okay, now in this taper bar some distributed forces are acting, which is this one, which is equal to 8 Newton per meter. Okay, so I believe this x, everything is given in meters, and then addition to this distributed force there is one point force which is acting, and it's not acting at the end but it's acting somewhere in the middle. Okay, which is at the position x is equal to 5, and the magnitude of that force is 24 Newton. Okay, and the next thing is there is no force acting at this end, so whatever the force acting is 0. That's what they have mentioned. Now we need to solve this problem using finite element method. Okay, so and particularly they have mentioned that we have to solve this method by using finite element method by considering only one element. Okay, and that one element is a 3-noded element. Okay, so 3-noded single element. So that's how we need to use this. We need to consider this whole thing as a one element, and it has to have 3 nodes. So one is over here, one is over here, and there should be a node at the middle. Okay, let's say it's going to have that value when x is equal to 4. Okay, fine. Now how to solve this? So here we put the node. We don't have to discretize into elements because they have asked us to consider only a single element, and in that element we have also put the nodes where they are going to be, right? So one is here and one is in the middle and one is at this end. Okay, now I have to come up with a shape function. So I have to assume how this u is going to vary along x, right? So for that I'm going to come up with a shape function, and here since it's given that we are going to consider this element as a 3-noded element, then I will have to assume the appropriate shape function for that element. Okay, so which are this n1, n2 and n3. Okay, and remember the shape function has to be such that when I substitute x, say for this one, when I substitute x is equal to 2, then it should give 1, and when I substitute x is equal to 4 or 6, which are the other nodes, then it should give 0. Okay, you could verify it. When x is equal to 2, then this will give 1, and when x is equal to 4 or 6, this will give 0. Okay, the same goes for this one as well. So when x is equal to 2 or 6, this will go 0, and when x is equal to 4, this will give 1. Okay, so you could also verify n3 as well. So fine, so we have shape function for this element. Okay, 3-noded quadric element, And now using this we need to calculate the stiffness matrix and force vector. But in order to calculate the stiffness matrix, we need one more vector or matrix, which is called B matrix. So that is the one which we need to identify next. So this is the definition of B matrix, right? So we have to differentiate this shape function with respect to x, and we need to calculate this vector, and if we do that, we will get this is the vector, where this is a first element, this is a second element, this is a third element. Okay, so that's a vector which is corresponding to this element. That's what this one represents. But anyway, it doesn't matter, because this whole domain is just a single element. Okay, that is just for this example problem. Okay, now I know what is this B matrix, and then I'm going to calculate the element stiffness matrix, which turns out to be the global stiffness matrix. Okay, so the element stiffness matrix is given in this form, and if I substitute my B and A, which is 2x, right, and then Young's modulus, which is also given, and if I do that, I will get it in this form, and if I multiply these things, I will get a matrix. Okay, and now by integration we mean integrating these each component of this matrix. Okay, each component of this matrix, which will provide me the stiffness matrix, which is corresponding to this element. But in order to convert that into a global stiffness matrix, we have to use this LE, right? That scatter matrix or the assembly matrix. But anyway, this whole domain is considered as a single element. We don't have to worry about that mapping. So this itself is a global stiffness matrix. Okay, so now we have to do the integration for each component, and we are going to do that integration using a numerical method. Okay, so how are we going to do that? So if we see, we are going to use Gauss quadrature. Okay, so how are we going to use Gauss quadrature to do the integration? Let's see, we have to choose how many points, whether we are going to use a 2-point Gauss quadrature, 3-point Gauss quadrature. That depends on how exact my solution needs to be, right? And if you see here, this is a what is the max, the highest order of x. So in all these equations, we could see the highest order of x is 3. So everything is a cubic polynomial, right? So in that case, I have to come up with a Gauss quadrature procedure, which could give an exact solution of cubic polynomial. It is not necessary, but I will get more accurate result. That's what. Okay, I could also use a Gauss quadrature procedure, which could solve for quadratic second order polynomial, but here I am just going for a Gauss quadrature procedure, which could give an exact solution for a cubic polynomial. Okay, now if I expect it should be able to solve a cubic polynomial, then I have to have at least 2 points in my Gauss quadrature procedure. Okay, that comes from this equation. So if I have to have at least have to have an exact solution for at least a cubic polynomial, then I have to have the number of Gauss quadrature point which should be more than 2. Okay, so and then the procedure of using this 2-point Gauss quadrature is as follows. So f of x dx, which is equal to then I will change from physical domain to apparent domain, or also known as mathematical domain. Okay, and if I do that, I'll get it in the form of zeta. Okay, and my limit goes from -1 to 1. So accordingly I have to choose the relation between x and zeta. Okay, and this integration I could solve using this some weight into the value of the integrand at some particular zeta, which is one of the Gauss quadrature point, and I have to do the same for other Gauss quadrature point. Okay, and for this 2-point Gauss quadrature point, what we need to remember is what is the weight and at which Gauss quadrature point I am going to evaluate this integrand. Okay, so if we look up the table for this 2-point Gauss quadrature, it turns out that this weight W1 and W2 is equal to 1, and this zeta 1 is equal to -1 by root 3, and this zeta 2 is equal to 1 by root 3. Okay, and this j, we have this j which actually comes, which is a Jacobian value, which actually comes from changing this dx to d zeta. At that time we will get this j, which is this 2. Okay, fine. And if we do this, we will if we evaluate this, we will get the value for this integration. And I have to use, if I do that, for the first component I am getting some value, and if I proceed the same procedure for other components, I will get this matrix. Okay, and it's a symmetric matrix, and remember the stiffness matrix is always symmetric. Okay, so stiffness matrix will always be symmetric, and if it's not symmetric, then you could check, there might be some problem and you could verify it. Okay, but one more thing, the stiffness matrix for advection problem, it will not be symmetric. That's one more thing. Okay, right, so now we have got the stiffness matrix. Now we need to calculate F matrix, right? So that force vector which consists of two components, one is body force and another one is surface force, right? Let's first consider the contribution due to body force. Fine. So now and this is the equation which is for the distributed force, and actually we have also have to consider this point force which is at this point, right? But right now let's ignore it. Okay, and let's just focus on this thing. Later I will tell how to calculate this one. Okay, how to calculate the contribution for a point load. Okay, fine. So if you see this one, this is known, and what is this B? B is just the body force which is uniformly distributed. So I'm going to use which is, I think it's been given as 8 Newton per meter. So I'm going to use that value in the place of B, and if I do the integration, I will get, sorry, if I do the multiplication, I will get it in this form, which I have to integrate. Okay, and forget about this part. Okay, forget about this part, and if you do the integration, then you will get, you will get this thing. Okay, and finally once again you will be using the 2-point Gauss quadrature. Okay, and if you do that, finally you will end up with this vector. Okay, now let's see how to account this point load. Okay, this point load, we can treat that as a distributed load. Okay, the only thing is it's like it's been distributed such that it's zero everywhere, and it's very large, it's intensely distributed at this particular point. Okay, so I could assume this distribution using a special function which is a Dirac delta function. Okay, so the Dirac delta function will shoot up at one point and zero at every other point, right? So that is the function which I am going to assume here. So here that function is p into delta, which is the Dirac delta function, delta of x minus 5. Okay, so 24 into delta of x minus 5, that is the force I am going to account in the place of b. Okay, and if I assume that, and if I do this integration, okay, then what will I get is this. Okay, you could verify that. So I will get this one, and that will provide me, finally that will provide me this vector. Okay, and the sum of these two vectors is the total body force. Okay, now there is something called a surface force, right? And the surface force, if you see, I will account only at the place where the Neumann boundary condition is given. So I can assume the surface force at this point is 0, the surface force at the center node is 0, and the surface force at this node is t bar, which turns out to be, for this case, is also 0. Okay, and therefore I don't have to worry about the surface force. And finally this is my total externally applied force, but at node 1 we have additional boundary condition, therefore we do not know the exact force applied at that point. So we introduce that uncertainty by introducing this R1, and then now we have finally this form, which is k into d, which is equal to this f plus r. Okay, and for this, using this equation, we will be able to solve for u2, u3 and r1. Okay, and once I solve for these things, then I can do the post processing, which is how this displacement and stress are distributed as a function of x. So in order to identify how u is distributed as a function of x, all I have to do is substituting, this is my u, right? That's how I defined and I have started with, right? So now all I have to do is I can substitute what is n1, n2, n3, and also now I know what is u1, u2, u3. Finally, after I substitute, I will get this quadratic equation. Okay, and if we plot this u as a function of x, So then I will get to know how this u is distributed in that bar. The displacement is distributed in that bar. Okay, and to calculate stress, this is the formula: sigma is equal to E du by dx. Okay, and if I do that, I will get this one, and once I plot sigma, which is this function, as a function of x, I will get to know how that sigma, the stress, is being distributed. Okay, so that's how we do the post processing. So, and that's how we solve the stress analysis problem using finite element method. Okay, thank you.